Well, hi again, this is Bob, and we're over on page 393. This will be kind of a short lesson, and it's actually not unlike something we did back in section 7.1, where we were finding sample size when we were dealing with the sample mean. Excuse me. So we're basically doing the same idea here, and I think I may have written this at the close of the previous lesson, but this should look a little bit familiar. We've got this formula, and my pen is leaking a little bit here, but we were talking about the correction or the margin of error when we're dealing with sample proportions, and you may recall that we had like z sub alpha over 2, and of course that's when we set up our confidence interval, and times that we had p hat and q hat over n. So if you don't recall this, just go back, actually you can just go back to example 7.9 on the previous page there, and this was the correction that we used to add and subtract from our p hat value. Recall that p hat was something like the sample mean. So we added and subtracted a little bit, and that depended upon, of course, what p hat and q hat were and the level of confidence that we wanted. Well, again, this is the exact same idea. What they do is, because we're looking for sample size, and let me write that up here so we're absolutely sure, and sample size, of course, is n. What we want is we want to rearrange this formula right here for n. And it's just some algebraic derivation. We don't really have to worry about it. And when we do that, and I just lost my pen again here. When we do that, and you can just look at the very, as soon as about halfway down on 393, it says sample size for proportions. Then it gives us the formula, and it's p hat times q hat, and then that gets multiplied times on top z sub alpha over 2, and we have our error on the bottom. And recall that we set our error, how close we want to be, and then the whole business is squared. Okay, now we've got two situations here, and both of them are really nicely demonstrated by two questions. Sometimes we're going to, in some cases, they will give us p hat. They'll say p hat equals, let's say, for example, 0.38. Then immediately q hat would equal the complement of that, or 0.62. Okay, so that would be like the first situation. But what happens if they don't give us a p hat and q hat? Well, if you notice right down below toward the bottom of page 393, you'll see a table, and the table has p hat and it has q hat, and then it has their product, p hat, q hat. And if you notice, the product that is largest, now this is if they don't give us p hat and q hat. Notice they give you, like, they're all complements, 0.1 and 0.9, 0.2 and 0.8. The ones that multiply together to give the largest product are when both p hat and q hat equal 0.5, and that gives us a product of 0.25. Okay, so what the book's getting at here is whenever we aren't given p hat and q hat, we use 0.5 for both of them, because that makes, in the formula, that makes this p hat q hat the largest it can be, and we would rather err on the side of having a larger sample than not a larger sample. Okay, so of course, if we have quiz questions and test questions on this, which we will, I will give you a strong reminder about the situation, and you of course will, on the practice test, I not only give practice problems, but I also work them out in great detail. Well, anyway, as I mentioned, this is a short lesson, and we're going to finish the lesson off by looking at two examples. Example 711, which gives us p hat and q hat, and example 712, in which they don't give them to us, and we have to use 0.5 for each one of them. Anyway, let's take a look at 711. A researcher wants to estimate with 95% confident. Well, the moment I see 95% confident, I think of z sub alpha over 2, and of course that would equal 1.96 for its value. That is the proportion of people who do not have a landline phone. A previous study shows that 40% of those interviewed did not have a landline. Okay, so right away our our sample proportion is 0.40, and then of course our Q hat would be 1 minus 0.40 or 0.6 or 0.60 if you like. I usually try to get the data as I go along, and then the last thing it tells us, the researcher wants to be accurate within 2% of the true proportion. So that's our error, 2%. Now think about this. If they wanted a smaller error, maybe like 0.01, that's going to make a larger study size because, as you recall, the formula for N was equal to p hat times q hat, and then we had our z sub alpha over 2 over e, our margin of error. If the margin of error is 0.01, that being in the denominator here will make the product of z sub alpha over 2 divided by e larger. I should say when we divide, we get a quotient, so that would make the quotient bigger. But if we had a value for e like 0.10 or something, that would give us a smaller value for the quotient. In other words, the smaller that e is, the larger the squared expression becomes, and the larger that e is, the smaller the quotient becomes. Anyway, we've got all the information we need to set this up, and as always, please make sure that you work this out on your handheld calculator and can understand the steps and get the same answer. And of course, if there's any left over, we always round up. So our N would equal, I like to use parentheses, 0.40 times 0.60. Okay, then our z sub alpha over 2 was 1.96, and our error is 0.02. And when that's worked out, we get 2304.96, which we round up. I don't know why this thing keeps losing my pen, but when we round up, we get 2305. Not possible to survey 0.96. So 2305 will be, that's the number of people we will need to interview in order to, at the conditions stated and with a 2% error. Okay, well the last example, and I'm sure you'll run into a couple of examples like this. This is example 712. I just don't know what's the matter with this pen. Okay, example 712, it says assume that no previous study was done. Well, remember in example 711, we had a p hat of 0.40 and a q hat of we didn't have that at all. Yeah, that's right. I was thinking of the other question. Okay, but in 712, we have no p hat or q hat. So, and this situation could pop up all the time where you don't know, you didn't take a sample ahead of time, and so you wanted to maximize your sample size. And in this case, it reminds us from the previous page that when we have no p hat or q hat, we use 0.5 for each of those. And we saw how that maximized their product. So it's the exact same question as before, only since we don't have numerical p hat and q hat, we use 0.5. So, and again, our error is 0.02. Our z sub alpha over 2 is going to remain 1.96, and our we've already got our p hat and q hat. So let's see what we end up with here for our sample size this time. It would be n is equal to 0.5 times 0.5, that's our p hat and q hat, times 1.96 divided by 0.02, and remember the 1.9. Find out what 1.96 divided by 0.02 is, then square it, and then take that times either 0.25 or respectively 0.5 times 0.5. And this time when we do that, we get 2401. Okay, and notice that 2401 is a little bigger than what we got when we had a 0.4 and 0.6 for p hat and q hat respectively. Well, we expected a little bigger answer here because notice that 0.5 times 0.5 equals 0.25. And in the previous question, we had points, I'll put it in order, we had 0.4 times 0.6, and that equaled 0.24. So that's the difference. That's why the second question is a little bit bigger, is because when we use 0.5 times 0.5, it maximizes our answer. Okay, well, that should do it on the second part of this lesson here on sample size for proportions. Okay, so we had the sample size for when we're dealing with sample mean and confidence interval, and now we've had a sample size for proportions. So work the homework questions carefully. Make sure that you check your answers. I'll be back shortly with 7.4, the last lesson in Chapter 7. Thank you.